QSM, what is it? So basically, magnetic susceptibility measures the degree of magnetization of a material in a magnetic field. And it is computed based on the MRI signal phase of a gradient echo scan. And usually it has quite an elaborate pipeline to get this information out. So in the end, we have this quantitative susceptibility map, and we start from complex data phase, and we have to unwrap the phase, we have to background field to correct the phase because there are external sources that overlay this signal, and then we need to solve an ill-posed inverse problem to get this QSM. And what is it used for? So it's quite sensitive to all biometals, microbleeds, calcifications. It can help us with exploring contrast agent biodistributions, and it can also be useful in exploring demyelination processes. So here we see a simple example where QSM could be useful. So there's an active lesion, so a bleeding is in positive, so in white, a positive susceptibility, and there's a calcified, or there are calcified lesions in here which show up as negative susceptibilities. And if we look as a comparison to T2 star weighting, weighted image doesn't show it that clearly. Also potentially quite useful in multiple sclerosis because there we know iron accumulates after demyelination in microglia, and also people have observed slow iron depletion in normal appearing white matter. So QSM is quite useful, but how do we get it? So this is a simple toy example. So we have magnetic susceptibility distribution, so a little magnetic source that we put in the magnetic field. And what we get is, when we apply a magnetic field, is we get this magnetic field perturbation. So this looks like this dipolar pattern. And it's basically our susceptibility source disturbs the magnetic field. And when we measure it in MRI, we get something that looks like this. And it's the wrapped MRI phase, because the phase we measure between minus pi and pi. So when we hit the boundaries of pi, then we wrap back to minus pi, for example. So that's why you see this wrapping, and it's not a continuous function as we see it, as it is in a real physical way. So the first thing we have to do is we have to unwrap it, and then we have to solve this inverse field to source problem. And now you can think of this problem as, if we know our source distribution, we can simply compute the forward model, because this, we know the relationship. So we just know if we have a source, there is a dipole kernel that describes that. So I will show that in a minute. And in order to estimate which source caused this field perturbation, we currently use iterative procedures. So we simply assume a source, we propagate this forward, we compute the difference, and then we minimize this in the least square sense. So that's our current procedures. And we call this inverse problem, but it's computationally quite expensive and has its problems to solve it. So that's why we thought, let's use deep learning for this, because it can approximate any function, and we call that deep QSM. And how did we do this? So we did not use, I think this is probably one of the differences to the talks we already saw today. We did not use measured data to do this. We actually simulated data, because the problem is, we can describe that. So what we did is we started simulating some simple shapes. So similar to the toy example I just showed you, just a couple more, because it doesn't like background. So if most of the image is background, the network will not learn. So we put a lot of these structures in there. Then we know our dipole kernel. So this is the mathematical description of this convolutional, or of this dipole kernel that we convolve our data with. And then we get our simulated magnetic field perturbation. And then what we did is we simulated lots of examples of these. And all of these images are three-dimensional, because as you can see, it's X, Y, Z. So this is a three-dimensional problem, and you cannot solve it on a single slice, because you miss crucial information from the other slices. So all of these images are 3D blocks. And then we generated 91,600 of these blocks. And in the beginning, I didn't know how much data I need to train. So I simply generated as much data as I could, and then my disk allocation was full. So that's how I ended up with 1,600. So that's one way of finding a hyperparameter. And then we simply trained it. So then we said, okay, this is my input and this is my target. And we trained a UNet to do this. And how does it perform? So now we simply simulated new data. We convolved it again, got the phase. And then here I have two established toolkits, STI, ALSQR, this is an iterative procedure, and MEDI. And these, I would say, are the two of the state-of-the-art methods that are very good and accepted in the community. And then on the right side, we see DeepQSM. So these are the outputs when I put this phase in these toolkits. So we see that DeepQSM generates something quite close to the simulation that we put in. When we look at the difference to simulation, it's good to see that all of them make some mistakes. So we see there are some, for example, here at some edges where the network is wrong. But it's also good because it shows that we probably don't overfit to the data. So we haven't learned the data. And also it's an ill-posed problem. So you would expect that there is no perfect solution to this problem, because if you want to solve it perfectly, you need multiple orientations. This is called Cosmos. And then you can solve the problem analytically. And then you don't have this ill-posedness. But here we have only one orientation, so there has to be some error. And then, remember, we just trained on shapes. So we thought, what happens if we use a real brain data set that was actually measured? And this is the phase of this brain. It's already background field corrected. And when we use STI, MEDI, and DeepQSM, we see we get quite similar results. However, there are some differences. For example, MEDI, in this case, I didn't have a very high regularization of this model term, so we get a lot of streaking. So MEDI, in this case, took the data more serious than its model, and then that's why it ended up with some streaking artifacts. So basically these dark spots here, and you see it later also a bit more clearer. So we call these are artifacts, and these are due to this ill-posedness of this problem. And STI is quite similar to what we get in DeepQSM. And then to investigate these effects a little bit more, we scanned 27 subjects. And now here we see a group result of a group template. So I simply averaged all of these 27 subjects so I can look at the artifacts on a group level. And what we see here is, especially in this coronal plane, we see these artifacts quite nicely. So these black streaks, this is what we call the streaking artifact, and also here you see it quite nicely. And even STI suite, where we didn't see it in the single subject, even here I think I can see some streaking. But when we look at DeepQSM, there is almost no artifact there, and it seems that the network found a very good regularization for this problem, for this ill-posed problem. But we also see that we lose some contrast. So in comparison to these two others, we have we have a lot less contrast, and this could be that the network is over-regularizing there. That could well be. And now I want to switch to the demo. So theoretically, if you open this demo, you should get in Google Colab, as we already saw today. And then here I have to make a disclaimer. So the code I'm showing today is not the original DeepQSM source code that we used in the paper. So I wrote it newly for the OHBM educational course, because actually a lot of the code complexity is reading in the data, shaping the data, and running it on a GPU cluster, and all of this is not really necessary for here. So I just wrote it from scratch to make it more easy to understand what we're doing. So the first thing I'm doing here is I'm mounting my Google Drive, so I can actually store my information across sessions. And I created a folder in here, DLQSM, so this should happen also in your Google Drive, and then you can look at the data later. And then if you're following this live, you need to uncomment these two lines where we have to download the reconstruction challenge data. So there was 2016, the QSM community came together and said, we want to compare these different QSM algorithms, and they came up with a reconstruction challenge. So we're using this data to test our trained network. And then this is just a function to plot a three-dimensional data set. And then we are looking here at the reconstruction challenge data. So let's have a look how this looks like. So here we see, this is the phase, tissue phase. So you see it's blurry, and it doesn't really look like a quantitative susceptibility map. And here we see, I called it gold standard QSM. So this is a multi-orientation reconstruction. So we actually can solve that problem analytically, but of course clinically that's not feasible. You can't rotate your patients in the scanner easily. So that's why I call it gold standard QSM, and also it's not perfect, so we know also this model has its issues, but yeah, we should see something like these bright structures in the center of the brain, and you see it's a lot less blurry, and this dipole effect is removed. So that's what we're aiming for. Now, let's simulate data. So this is a function that I also simplified from what we used in the paper. So here I'm just using some rectangular shapes because they're much faster to generate. And when we look at them, we see them here. So it's a three-dimensional block, 320 by 320 by 320. And I have 800 rectangular shapes in there, and then they're three-dimensional. And then this is how this looks like. And now I need to apply my dipole kernel. So this is this dipole kernel you saw on the slide. So 1 over 3 minus this dipole formula. And when we generate this dipole and look at it, we can see how it looks like. So this is the dipole effect in Fourier space. So this is basically how we filter our data. And this is the effect we want to undo. So now I'm computing the forward convolution of my simulated data to get this artificial phase data. And that takes a while. Yep, so basically I'm going in K-space, and in K-space, or in Fourier space, and in Fourier space, I'm multiplying with the dipole kernel because convolution in image space is a multiplication in Fourier space. And then we can look at this. So this is the simulation. So this is, again, this is the output after convolving with the dipole kernel. So you see here I had, so here below you see the input, these rectangular shapes. This is our simulated ground truth, and here we see the convolution, or the output of the convolution. You see you have all these blurry things, and things are, it's hard to distinguish. So you couldn't say that this thing was black or had this value because of this, this effect. So now we are training a model to undo this effect. So the first thing we have to do is, and this is again similar to what we already saw in the other presentations, on the GPU we don't have that much memory. So what I chose here is I take patches, three-dimensional patches from this big data set, and here I generate 500 patches, and I make them 64 by 64 by 64. So let's have a look at this. This should be quite fast. And then we can look at patch index 44. And here we see this is the ground truth, and this is after convolution. And this is what we will use for training. So the input will be this blurred pattern, and the output will be, or the target will be this ground truth. Okay. Then I thought for this tutorial I used the newest TensorFlow because I wanted to play with some of the new features. So this is 2.00 alpha 0. So theoretically, you should be able to run this also in a few more weeks when the final version comes out. And I'm just testing that my GPU is here. So I'm using in a runtime with GPU. And what I'm defining here is, so we saw today already how we build up these UNets. And I'm lazy and I don't like copy and paste, so I copied from this example. There's this pigs-to-pigs example from Google. This one, yes. So tutorials generative and pigs-to-pigs, and they have a very nice way of generating a UNet where you define the downsample function first, you have the initializer, and then you add a convolutional 3D layer. Then you can decide if you want batch normalization or not, and then you apply a leaky ReLU unit. So this is our downsample, or one downsample block. Then I'm testing that this works and get everything in terms of shapes right. So I have a 64 cubed volume, and then the first dimension for this TensorFlow model is the batches, so how many examples I show per training step. And the last dimension are the channels. So you can, currently I only have one channel, but if you have multimodal data, then you could have multiple channels. Then I'm testing this downsample part. So I'm giving it one of my input data, and I'm checking that I get the right dimensions out. So it downsamples from 64 to 32. And I made 8 filters, so I see that the filters are now where I'm expecting them, and I had one example. So that all works out. Then I have an upsample part. The upsample part, the only difference really is that I have not a 3D convolution, I have a convolutional 3D transpose. And I also apply dropout on the upsample part and only in the center of the unit. And also then there's a value. So let's execute this. And then if it's not tested, it is broken. So let's test it as well. Yes, okay, so that works. 64 by 64, and then we get 8 filters. So we can upsample again. So I gave it the downsampled result to test if I can get back my 64 shapes. Okay, so this all looks good. Then I tried to get a model that trains while I'm speaking, and I couldn't get anything to work with training times less than an hour. I think the problem is that it's a 3D data set, and it takes a lot of time just to train. With a 2D data set, I think it could have worked, but 3D I just couldn't get to work. So I trained it with about 500 epochs, so it takes a while, and then I'm saving the data sets out every 20 minutes, so that in case my notebook session expires, it still runs. Or I can still look at the results later. Then here I'm defining the architecture, so I'm parameterize the filter base, so how many filters I want, the kernel size, and then I'm basically downsampling until I'm at the base of the unit, and then I'm creating an up stack where I'm upsampling again, and the initializer, the last layer of the network, and then the concatenation layer. I'm defining the inputs. So here's an important thing, because I want this thing to be fully convolutional. So if I wouldn't put none here, but the actual input size, then it wouldn't be able to then carry us complaints. So this gives me the possibility to train on 64 by 64 by 64, but then apply it to 160 or 320 if I want to. Yes, then I'm setting up the skip connections, and also for upsampling, and then I created this model. That's basically the unit, and then I'm compiling it with the mean squared error, and an optimizer I used Atom. And then here we can look at this model, so we see the input, then we see our sequential, where we are going down, then our concatenations, and then we're going back up again. And we have 3.5 million parameters. So let's quickly test, what does the network do? So now this is defined, right? It's initialized, but we haven't trained it. So what is the output when we don't train it, just as out of curiosity? So this is the input, this blurry thing. This is the susceptibility distribution that we want. And when we give this as an input to the network, we get this as an output. So that's good. So we're not getting anything nonsense, and it also doesn't give us back the input. So it's just giving us a blank thing. And then we can train. So I will skip the training now. And I will load a checkpoint that I created beforehand. And then we can look at what the training is. So I trained it for 500 epochs, and we see the error pretty quickly goes down, and then it's on a downward trend for a few epochs. And then the first question, did we actually learn the training data? So just as a sanity check, so I'm giving it one of the training data sets again. So it has already seen this during training. This is the input, this is what it should predict, and this is what it predicts. So we see that the network is still not perfect. So even after training 500 epochs, it has an overfit to the data. So it's not reproducing exactly the training data. But we also see that it's still doing some mistakes. But when we consider that this was the input, and it recovered this. That's not too bad. And also we have to think about it. It is an ill-posed problem, so there is no perfect solution, or it shouldn't produce the perfect solution. Then the question is, what happens, so this was on one patch, what happens if we give it now the whole data set, the big 320 data that I generated in the beginning. So just to see, this is 320 cubed. This is the ground truth that I'm expecting, and this is what the model gives me. So here we see that in some areas it is pretty off, but we also see that it recovered some of the details quite nicely. And can it work on brain data? So this is where I was hoping that it works a little bit better. And here we see the input, we see what we ideally would like to have, and this is where we currently are. So we are on the way to the ground truth, but we are not yet there. And yeah, but if we compare that, it's a lot less blurry, and we start to see the right contrast that we would expect for QSM. Yeah, and then I just added another model, a slightly simpler model. So if you want to run that, and then you can, as a last thing, I just have the influence of the hyperparameters. So you can play with this a little bit, and then we can compare the two models and see that in this case, the model one I showed you first, because it was a much more complex model, has a better error rate than the second model that was a much simpler model. So you can play with this. And then I'm going back to my slides, and yeah, that's just as a summary. Yes, so it learned to basically take this input, produce this output, and it's quite close to ground truth. But yeah, in order to get better, we need a lot more examples and a lot longer training time. And yes, and also on brain, we see it did get closer to the ground truth, but it's not perfect yet. And then I wanted to present another thing on top of this. So now we only solved the inverse problem of QSM. So the next thing is the background field correction. And we used a very similar approach to what we already showed with deep QSM. We called it SharkNet. And what are we doing there? So here we're not simulating susceptibility distributions per se. So we're actually simulating background sources. So this is a frame around the brain, and we simulate sources that are outside of the brain, and that they generate fields that look like these background fields that we see in QSM. And then we overlay them on a synthetic brain, and this is what the input would be to the network. So the question was, can we also remove this background field with the same technique? So we, again, simulated 1,000 source configurations. We got 1,000 simulated background fields, and we overlaid that on these synthetic brains. Then, again, these are all three-dimensional patches. So we cut 1,000 crops per 1,000 simulations. So we ended up with 100,000 3D patches. And then we thought, okay, let's test it. So we have this synthetic ground truth brain. This is a simulated background field that we overlaid on top of this. And we see that it's very hard to see the details below. So you see it's really, this background field is messing with us, and we couldn't use this to directly invert the problem. So we need to remove that first. And this is SharkNet, so this is the output of the network. We can, when we compare this to the ground truth, we see we are quite close. We managed to remove this low frequency background field. And when we compare to established methods, so sharp, resharp, and vsharp, are all established methods, and we see, for example, sharp filters the image quite a lot. So, for example, here you see a small dark band that actually is true, and that should be there, because also structures inside the brain cause low frequency fields, so we cannot just spatially filter it. But yeah, with sharp, we lose this information, but resharp and vsharp are a little bit more sophisticated, or extensions to sharp, and they keep this information. Since this is simulated data, we actually get real error measures. So when we look at SharkNet versus ground truth, we see the errors are quite low compared to the established methods, which is very nice and good to see. And we also tested it in a real in vivo case. So this is measured data where we don't have ground truth, and this is the real background field of a real volunteer. And we see here most of the background field comes from the sinus areas and then affects this part of the brain, also the temporal lobes. We have lots of this background field. And we see that all methods manage to correct this background field. And then Of course, it's hard to say what's true, but we could say from our simulations that we saw that sharp is removing a little bit too much. So we see we have some of these dark structures that we kept here, but that are gone here. And yeah, that's this. And I think with this, I thank you for your attention, and I'm looking forward to questions. Thank you.
You mentioned overfitting several times, but if you're using simulated data, and I don't recall you mentioning any noise, what's the problem of overfitting in that context?
It shouldn't be a problem. So yes, that's why we chose simulated data, because we would see it if we overfit on the simulated data. And then if it doesn't work on brain, it would be quite obvious. And we haven't trained with noise, but that is a idea that we should do.
Why did you not add noise?
Why we didn't add noise? Just because it was working without noise, so we didn't bother with it. But it would make a lot of sense.
Overfitting is usually overfitting to the noise. So I'm wondering if you can even have overfitting if there's no noise.
That is true. Yes, well, you could. I guess you could overfit to, if you don't add noise, you could probably learn the simulated structures.
That would have been my next question. Does it matter? Have you checked if it matters what kind of shapes you train on?
Not really. Yes, exactly. So we played with this a lot, finding an optimal training case, and it seems to work with almost everything. So that's the funny thing. Where it doesn't work is if you have mainly background, then the network learns to predict background because that minimizes the error nicely. So the image has to be full with stuff, and ideally I think the spatial frequencies have to match what we see in the brain. So I guess you could even just simulate random noise and train on that if that has enough structure for the problem.
But your geometric structures don't really match up with anything you see in the brain, right?
Well, when you look at the spatial frequencies, it does, because we have edges and we have things. So from this perspective, it does match. So we represent structure. So I don't think that if you have something that's completely unstructured, it wouldn't be able to learn that. But I think there's a lot of room for improvement there. So if you come up with a better way of simulating data that represents brain data on a spatial frequency level, I think that would be quite nice to optimize the training. Yeah.
Thank you.
Okay, thank you.